All right, so 8.5 was kind of our introduction into probability. Basically talking about like figuring out how many of an event can occur, how many times an event can occur, which ways it can occur, that kind of thing. Today we're going to get into what's the probability of a specific event occurring. So number 1 said, determine the number of ways in which a computer can randomly generate a pair of distinct integers from 1 to 15 whose sum is 20. So first of all, think about a computer. Is a computer, do you have to worry about replacement or non-replacement with a computer that's random? No. It's always going to be the same set, right? So it's always pulling from the same set. It's not like numbers are taken away and then you have to worry about the non-replacement issue. So integers from 1 to 15 whose sum is 20. What combination of integers gives you a sum of 20 that fall between 1 and 15? 5 and 15. 6 and 14. 7 and 13. 8 and 12. 9 and 11. 10 and 10. It's the same set of numbers both times, right? So you can get 10 twice. Is that a different way than getting a sum that is 15 and 5, 14 and 6, 13 and 7, 12 and 18, 11 and 9, and 10 and 10? Everything's the same everything's different except 10 and 10. So it is all of these, and then it is the reverse of this. So that is 1, 2, 3, 4, 5, 6. The reverse here would be 7. Reverse here would be 8. Reverse here 9, 10, and 11. So there's 11 different ways for a computer to randomly generate two numbers in which they sum to 20. Number 2 says telephone numbers in the U.S. have 10 digits. How many different combinations are possible within each area code? Note, a local phone number cannot begin with 0 or 1. So the telephone number has 10 digits, right? What's true about all the ones within an area code? The first 3 are already the same, right? So while it's 10, yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're not worried about the first 3. The first 3 are already set. So for the rest of them, it has to be a single digit, which we established yesterday was between 0 and 9, right? Except what other piece of information did they give you have to worry about? Can start with a 0 or a 1, which means that first spot, what's the number that goes there?
2.
That's how many you're eliminating.
8. Are you talking about the number of options? Or?
Yeah.
Oh, so 8.
8, yeah. So there's 8 choices of numbers between 2 and 9 that could go there. The next one would be how many? 10 and 10 and 10 and 10 and 10 and 10. So 1, 2, 3, 4, 5, 6 zeros, which means that there is 8 million possibilities within an area code. If it had said not within an area code, like you're talking worldwide, then you've got those first 3 to deal with, right? Because that could change as well. Carlos.
I don't understand why you're taking out the first 3.
Because you're within an area code. Within an area code, the first 3 are the same for everybody.
Okay. So it's like it doesn't give you a specific area code, you're just like...
Yeah.
Okay.
It just means I'm eliminating those first 3 because those first 3 are already set. All right, number 3 said how many different ways can 5 couples pose for a prom picture? Assume each couple stays together. So although there's 10 people, how many spots can I rearrange? 5. They are 1. They count as 1. Okay? And if it is, couple 1, then couple 2, then couple 3, then couple 4, then couple 5, is it different if it's couple 2, then 1, then 3, then 4, then 5? Yes, which means order matters. Yeah? Yes? When order matters, what is it called? We talked about 2 different letters yesterday, a P and a C.
P.
The P, which is permutation. And to find the permutation, I do what?
N over N minus R.
That's if you're taking a couple at a time, right? So if it said, how many different ways can I pull 2 couples at a time, then I worry about the R. But if it's just how many different ways can I rearrange the 5 people, and factorial, which in this case is 5. So 5 times 4 times 3 times 2 times 1 is 720? 120? Is that right? 3, 2, 1, 20. Times 6. 120. Yeah, you're right. Questions so far? All right, so number 4, find the number of distinguishable permutations of the letters W, E, E, K, E, N, D. So for these, I need to figure out how many total letters there are, right? And then put it over anything that repeats. So how many total letters are there? There's 7 total letters. That's going to be my numerator. And then W only appears once. Technically, that would be a 1 factorial, but that's 1, so I don't even have to put it underneath. How many times does E occur? 3 times. So I've got this over 3 factorial. And then I already accounted for the E. How many times does K occur? Once. I don't need it. E is already accounted for. How many times does N occur? Once. And D? So the only one I really have to include is that 3, because this would be the same thing as 1 factorial, 1 factorial, 1 factorial. So I get 7 times 6. That's a 6 times 5 times 4 times 3 factorial over 3 factorial. Those cancel. And I get 42 times 20, which is 840. Questions on that one? All right, and then number 5 says you can answer any 12 questions from a total of 14 questions on an exam, and how many different ways can you select the questions? So if I'm pulling the first 12 questions, is it asking me how many different ways can I rearrange the order of those questions, or is it just saying how many different ways can I pull 12 questions? Just collecting 12, which means what? P or C? C. This is a combination, okay? Whether you picked 1 through 12 or you picked 12 through 1, it's still the same set of questions. So I use combination here, which is C. N would be 14. R would be 12. So I do 14 factorial over 14 minus 12 factorial times 2 factorial. Nope. Times 12 factorial. Working ahead in my head. 14 over 2, God bless you, times 12. So 14 is 14 times 13 times 12 factorial. The 12 factorial cancels. 14 divided by 2 is 7, and 7 times 3 is 91. Questions on that one? Emily?
How do you know that it's not combination?
It will usually say something about order. So in how many different ways can the questions be done, in how many different ways can they be taken in order? Or in how order matters. Literally, usually there's something about that. In what order can I put these items? All that stuff would be permutations. So notice I didn't use the calculator that entire time, okay? Pretty much every question you have on your test can be done with or without a calculator. So it's not a matter of this is the type you're going to get without and this is the type you're going to get with. It's just the size of the numbers. So I could give you a permutation that has smaller numbers that you need to be able to do without a calculator. Or I could give you a permutation with larger numbers in which you'll have your calculator for. Make sure you know how to do both. Okay, so the calculator is really there just as an aid to help your speed, not so much as it can't be done without it. All right, okay, so now we're talking probability. So we go from building just the sample set to what is the probability a single event will occur within that sample set. So your answers for probabilities are going to be like fractions or decimals or percent, okay, instead of just a single number. So any happening whose result is uncertain is called an experiment, okay? So you'll see a lot of just this vocab terminology. The possible results of the experiment are the outcomes. So if the experiment is flipping a coin, then the outcomes could be heads or tails. The set of all possible outcomes of the experiment is the sample space, which would literally be heads and tails. Those would be the sample space. And any sub-collection of a sample space is an event. So getting a head from flipping a coin, that would be your event. So for instance, when a 6-sided die is tossed, the sample space is represented by the numbers 1 through 6, because if there's 6 sides on it and 1 number's on each side, there's 6. For the experiment to be fair, each of the outcomes has to be equally likely. So in order for an experiment to be fair, you're assuming that it's not like a weighted coin. It is 50-50 to flip it, heads or tails. It is rolling a die, so it's 1 to 6. Okay, if it's pieces of paper in a bag, each one would have an equal amount of color or whatever it is that you've got going on, equal number on it. Those would be equally likely. So we're just identifying the sample space for each of the following. So yesterday and the day before we were talking about how many elements would be in the sample space. Now you're identifying what those elements would be, which you did in a couple of questions. But so if one coin is tossed, what are the possibilities that could occur? You can either get heads or you could get tails. If 2 coins are tossed, what are the possibilities? Heads and heads. Heads and tails. Tails and tails, and tails and heads. So remember we talked about this yesterday. If you want to know the number, you would multiply the number of events, the number of elements in each event. So if it is one event and there are heads and tails, then there should be 2. If there are 2 events, one is tossing the coin the first time, one is tossing the coin the second time, and each one has 2 outcomes, then it's 2 times 2, which is 4. So if 3 coins are tossed, how many outcomes should I have? 3 times, how many different outcomes are there in each one? 2. So what am I looking for? 6 total options. So think about, it could be heads, heads, heads. It could be tails, tails, tails. It could be heads, heads, tail, heads, tail, heads, tail, heads, heads, tail, tail, heads. Wait, did I just say 6? No, there should be 8.
Yeah, there should be.
Yeah, 3 coins are tossed. It would be 2 times 2 times 2, not 2 times 3. The event, right? The chances of an event occurring the first time, the sample space would be 2. The second time would be 2. Third time would be 2. 2 times 2 times 2 is 8. So, because there can also be HTT and
THH. Yeah. T. No. Yeah. THT.
THT. That's what we're missing.
Exponents then, please?
It doesn't matter. You're either multiplying the number because it could change. So it depends. Like, are you tossing could you be flipping a coin and then rolling a die? So flipping a coin would be 2 options for that one. Rolling a die would be 6. So the combinations there would be 2 times 6, which is 12.
Okay. Can you repeat what?
The options or the number? It should be heads, 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 tails, heads, tails, heads, heads, tails, tails. Or tail, 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 head, head, tail, tail, head, tail, head, tails. It doesn't have to be in that order. You could do it in any order. But if you are tossing a coin 3 times, and each time it has 2 outcomes, then you do 2 times 2 times 2, which is 8 possibilities. Okay, so the probability of an event occurring is found by how many times the event could occur, that specific event, over the sample space. So you're setting up a fraction here. Every answer should be reduced. If it said to round it or what's the percentage, that's when you would change it. But most of your answers are going to change or going to stay in fraction format. So if an event E has equally likely outcomes and its sample space is S, which is how many different outcomes there could be, then the probability is the number of events over the number in the sample space. Because the number of outcomes in an event must be less than or equal to the number of outcomes in the sample space, the probability of an event must be a number from 0 to 1. So if I said, what's the probability of you getting a heads by flipping a coin? Okay, we would say that the options are either the ones we just talked about. Flipping a coin could either be heads or tails. That is 2 options. That would go in the bottom. The one we're looking for is heads. That only can occur once. That would go on the top. You're never going to get a question in which it could occur more times than your sample space. So your answers would never be bigger than 1. If the probability is 0, it's called an impossible event. So if I have a box of colored strips of paper, and there are red and green strips of paper, and I say, what's the probability of it being blue? It's literally impossible, right? There are 0 blue over how many strips there are. It would be an impossible event. However, if that box is filled with all red strips, and I said, what's the probability of getting red? Then it's going to be 1, because it's however many there are over however many there are. Most likely, those 2 events are not going to occur very often, but that's what they would be, impossible and certain. All right, so example 2 says 2 coins are tossed. What's the probability that both lands heads up? So I just pasted in with the sample space we already created, right? We said if 2 coins are tossed, then the options are heads, 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 tail, 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 heads. So my sample space is what number? How many different options are there? 4. The event I'm looking for it to occur is that both are heads, which happens how many times in this sample space? 1. So the probability of it both being heads is 1/4. The next one says a card is drawn at random from a standard deck of playing cards. What's the probability that it's an ace? Okay, so I put a picture like this again in files if you need it. You do need to know what's here. So you want to look at this deck. Obviously, there's 52 cards. There's 13 in each suit. There are 2 suits that are black, 2 suits that are red. The suits are spades, clubs, hearts, and diamonds. There are ace cards, which are not a number nor a face card. So when you start to see stuff like that, you'll know. A numbered card has a number on it. A face card has a face on it. So a jack, a queen, and a king are pictures of jacks, queens, and kings, which are all people. So they all have faces on them. Those are considered to be face cards. If the question is the value of the card, like if it's a high value or a low value, it will usually establish that ace is low or ace is high. Default, I would say, is usually that ace is low. But I know, like a question on your test, it will say ace is low. And then you know. Okay, so a card's drawn at random from a standard deck of playing cards. What's the probability that it's an ace? So what is my sample size? 52 cards. That's going to go on the bottom. And how many aces are there? 4. And then I reduce 1/13. Obviously, they get harder. All right, mutually exclusive events. So 2 events from the same sample space are mutually exclusive when they have no outcomes in common. For example, a card being a 5 and a 6. A card cannot be both a 5 and a 6, so they are considered to be mutually exclusive. Not mutually exclusive would be like a 5 and a heart. So a 5 can also be a heart. That's a different scenario, which we'll get to in a moment. The probability of an event occurring that is mutually exclusive is literally the probability of the first one plus the probability of the second one. So if it says the probability of getting a 5 or a 6, then I would add the probability of getting the 5 and the probability of getting the 6. So it ups your chances, right? It should actually be easier to get a 5 or a 6 than it is to just get a 5 by itself. Does that make sense? So you want to pay attention to the words or and, because the word and makes it more difficult. To get a 5 and a 6 is a different scenario. So this says one card is selected at random from a standard deck of 52 cards. What's the probability the card is either an ace or a jack? Again, or is an important word here. So I need to find the probability that it could be an ace plus the probability that it could be a jack. How many aces are there in a deck? Okay, we could do 1/13 is aces. How many are jacks? 1/13. So that came from doing 4 over 52, just so we can 4 over 52. So this is 2/13.
But it won't always be like that. It might be different fractions. So.
Correct. That's why. So sometimes you might want to leave it the way that it is because it might reduce different.
All right.
But at the end, it's always reduced. Okay? If you were to literally think about your entire deck of cards and count the aces and count the jacks, there are 4 aces, there are 4 jacks. That would be 8 out of the 52, which would still simplify to be 2/13. Not mutually events. This is what we just said. So it's something like a 5 and a heart, okay? Or a jack and a red card. Those things can both happen. They can both not happen, but they can also both happen. So to find those, for an overlap, we do the probability of the first one plus the probability of the second minus the probability of both of them. So if this was 5 in red, I would say the first is the probability that it's 5, the second that it's probability that it's red, minus the probability that is a 5 and red. So you're going to see a lot of this little like union, intersection, okay? That's what that means.
Yeah, how would you do that?
We'll show you. It looks more complicated than it is. So a card is selected at random from a standard deck of 52 playing cards. What's the probability that the card is either a heart or a face card? So first, you have to read that and establish that this is mutually not exclusive. A heart can also be a face card. Does that make sense?
Yes.
So I'm going to do the probability that it's a heart plus the probability that it's a face card minus it's the probability that it is a heart and a face card. How many hearts are there? 13. So this would be 13 out of 52. How many face cards are there?
4. Oh wait.
So
sorry.
there's 3 in each,
There's 12.
which is 12. Good. How many hearts are also face cards?
24. Oh.
3. The Jack, the Queen, and the King of the hearts, right? So this is 25 minus 3, which is 22 out of 52.
Oh. That makes sense.
That was a very loud light bulb.
Sorry.
It's okay.
You got an epiphany.
I'm glad you're awake. So if I had literally counted up the cards on my deck, if I counted all of the hearts and I counted the face cards, I could not count the face cards that were also the hearts, but I'd get the same answer. Yes.
You don't simplify.
Yes, you simplify that. Answer's not done. Sorry, I got distracted by the light bulb. This should be 11 out of 26. Every answer should be simplified. All right, the last thing is an independent event. So 2 events are independent when the occurrence of one has no effect on the other. This is kind of like replacement and non-replacement. So for instance, rolling a die. If I roll a die, it doesn't matter how many times I roll the die. If I roll it the first time, it is totally separate than if I roll it the second time because it's the same odds. Same thing as flipping a coin, okay? Same thing as pulling something out of a deck and putting it back. Those would be independent events because you're starting with the same sample space every time. To find the probability of both, so now we're talking about an and instead of an or. So I want the probability I pull a 5 and a 10 with replacement. And those you multiply. So an or we add, an and we multiply. Okay, example 5 says a random number generator on a computer selects 3 integers from 1 to 20. What's the probability that all 3 numbers are less than or equal to 5? So this is definitely an independent situation because it's a random number generator from a computer. So the computer will start with the same set of numbers every time. So we need to identify what's the probability that it's going to be pulled the first time plus the second, or sorry, not plus, this is a times because this is an and, times the second time times the third time. So again, because this is all 3 numbers, this is an and scenario, which means multiplication. So the first time it happens, the sample set is 20 because it's the numbers 1 to 20. It is also 20 for the second time and the third time because this is an independent situation in which the numbers are not affected. So the probability that it would be number less than or equal to 5, that's 1 to 5, which would be 5. And it happens again for the second set and again for the third time. So if I reduce that, that is 1/4 times 1/4 times 1/4, or 1/64. So the probability that all 3 numbers are less than or equal to 5 is 1 out of 64. And hopefully that makes sense that would be less than if I just asked for a single time. So if I just ask for a single time, it's 1/4. But it is less likely to have the same event occur more than one time, which means that number should decrease. All right, that's the end of 8.6 part 1. We will finish tomorrow.